Okay, good. So this is the first class on part 4 of the new astronomy. Today we're going to be covering chapters 41 through 44, which is the opening of part 4, where Kepler is now, after studying how the physical power of the sun can move the planet Earth, is now going to apply that to Mars and eventually all the planets in his future work. I wanted to start off though by seeing if people had any quick questions from part 3, in particular on the end of part 3, from chapter 40, or about how Kepler's solar power work, because that's going to be very important for what we're about to do now in looking at Kepler's hypothesis for Mars. So to start off, does anybody have any? I've got some things that came in from emails or that seem like they're questions, but does anybody have any questions from part 3? Okay.
Hey, Jason,
Yes.
can you hear me?
Yeah, I can hear you.
Um, I don't have an explicit question on Chapter 40, but I would find it really useful if you could go over that chapter in a precise, in a concise way.
Sure. So let's just get a picture up here. So, but overall in part 3, okay, so, what has Kepler thought for, a long time? He's thought that the sun moves the planets. Now, just saying generally that the sun moves the planets, that's not enough to, you can't build up a whole theory based on just saying that. It's not very specific. But he's had the view for years that the speed of a planet depends on how close it is to the sun, because the sun is actually moving the planets around. So, what he did in the about halfway through part 3 is he said that if a planet moves according to a bisected eccentricity, meaning if it moves as though the sun, the planet's center, and the equant are evenly spaced between them, then its speeds at perihelion and at aphelion, when it's close and far from the sun, its speeds there are in proportion to how close it is to the sun. He expands that to say that's true everywhere on the orbit. He only does that proof specifically in chapter 32 at the apsides, but that's fine because his physical power isn't going to be equivalent to the equant. So here's his principle. This is what Kepler sticks with. It's not area time. That's really not a principle. Even at the end of this book, he's still not comfortable with that as being a principle. His principle is that the amount of time it takes a planet to move through, let's say, 1 degree of its orbit is proportional to how far it is from the sun. So keep that in your mind. That's the Kepler absolutely sticks to that. That's his primary physical principle here. The time it takes a planet to move 1 degree, or any amount you want, is proportional to its distance from the sun. That's the principle. The trouble is that the planet has a lot of different distances from the sun. In fact, its distance from the sun is always changing. So you have either, you got 2 choices then. You get 2 choices. One is that you can, where's the picture? Right. One is that you can try to add up every single distance of the planet from the sun, as you see in this animation. The trouble is, even if you wanted to add it up every degree, well, that's not very precise. If you broke up the orbit into minutes, you've now got 21,600 minutes in an orbit. So if you actually wanted to count and add up all those distances, it would be an incredible pain. So forget that. He says, well, maybe it's possible to use a geometric figure, an area, because an area can include an infinite number of lines. So, he looks at the area that would be formed by adding up all of these different, if we take and add up all of the different distances of the planet from the sun, and then arrange them in this shape that he calls this conchoid, then the area of the conchoid would be the sum of those distances of the planet from the sun. The thing is, he can't figure out what the size of that conchoid is. He can't calculate its area, and he uses as a approximation, although he's not happy with it and he doesn't think that it's true, he uses the where is it? Here's a picture of it. He uses the area that the planet is swept out. So from the sun to the planet, when it moved from here to here, the total area encompassed in that, that's like adding up all of the distances from the sun. It's not actually equivalent, but it's pretty close. And so Kepler ends chapter 40, he ends part 3 with area as being close to the amount of time that it took for a planet to traverse a certain amount of arc. He doesn't agree with it exactly. There are problems with it, but that's his rough approximation. Any other questions on part 3? Or any questions about that explanation?
What makes the area different from the sum of all the distances?
Okay, what makes the area different from the sum of the distances? Okay, this is a big one here. There's a couple of reasons that it's different. One is that the area, here, I'll show this picture here. Archimedes had a way of demonstrating why the area of a circle was, here's a way of showing why the area of a circle is pi r squared, for example. You take the whole circle, and you break it up into all these triangles. These triangles, if you put them all down like this, they form a rectangle. How tall is that rectangle? This is the radius of the circle. It's the same as the height of each of the triangles. How wide is this rectangle? Well, it's this half the circumference here. So half the circumference of a circle is pi times its radius. So this is pi r, and the height is r, which makes the area of the circle pi r squared when the circumference is 2 pi r. So that's very exact, and it works. There's a couple reasons why this won't work for Kepler. One is that for Kepler, the triangles don't come to the center of the circle. The triangles come to this eccentric point, the sun. What that means is that the base of each of these triangles, and if you look at this this picture on chat, you can click on the screen there. People who are watching it live, you can click on that view there, and you can get a good view of this. The triangles' bases are not perpendicular. They're not tangent to the circle. Over here, each triangle actually is sitting on the circle. And if you had broken it up infinitesimally, the base of each triangle is on the circle. Here they're not. Here the line from the center out to that point on the circle, it's not tangent. I mean, it's not perpendicular. The line coming from here to the circumference, it's not perpendicular to this tangent of the circumference right there. So the triangles aren't really, they're not sitting evenly on the base. That's one problem. Another problem is that we know that adding up all of the distances must be larger than the area of the circle. Right? The sum of the distances must be more than the area of the circle. And here's why. So for these 2 points opposite each other on the planet's orbit, if we added up the distances to the sun, it's longer than adding up the 2 distances to the center. If we had broken up the orbit evenly into, let's say, 360 degrees, here's another spot. That's not a very, this is not the right drawing to look at. On this one, let's say we also took these 2 points. If we're splitting up the circumference evenly, we'll end up having this point and this point. Again, their distances to the sun added up. Their distances to the sun added up are longer than both of their distances to the center. So if adding up all of the distances to the center makes the area of the circle, then adding up all of the distances to the sun has to be larger than the circle. So we know that the circle's area can't precisely measure the sum of the distances, and that shows up in the conchoid. one more thing about this conchoid. So here it is actually drawing out, and you can do this on your own. This is done on paper with a compass. You can do this yourself. You keep adding up all these distances. You put them together. That makes the real conchoid. Kepler compares it to a second one. And here you see there's two conchoids. The solid line is the one that actually corresponds to from the planet to the sun. The second conchoid with the dashed line is when we shorten the length in a specific way. It's when we, here it is. So here we have, for example, point G on the circumference. We could have gone to the sun, but instead, if we draw a line through the center of the orbit, and then drop a perpendicular from the sun to that center, if we take the length GQ, and if we did that everywhere along the orbit, GQ is part of this dashed line. It's not as far out as A. If we do that, we will make the second conchoid, represented by the dashed line. The area of the second conchoid that only goes out to the dashed line is the area of the circle, because if we keep using these distances that go on these perpendiculars through a diameter, these diametral distances, then the one on this side plus the one on this side average out to being the radius. So if we use all those diametral distances, then the area of the conchoid will be the same as the area of the circle. So the dashed conchoid that goes right through this point here, this is the area of the circle, and Kepler says that there's a lunule, the space between the two conchoids, and that's the specific size of the disparity. He's going to look at that when we get to chapter 43 as we move into part 4. Kepler is going to figure out how big is that lunule and how far off are we if we use the areas swept out on the circle as a way to approximate the actual sum of the distances of the planet from the sun. And we'll be able to say how far off are we if we use the area to measure the time instead of adding up all the distances. Does that answer your question?
Yes, thank you.
Okay. Okay, well that was, unless, if there's another one, we can take one more on part 3. Otherwise, I want time to get into part 4. So, going once, going twice. Okay. And we can talk about it on the Hangouts in between classes, too, if you have more questions, or farther back, which I know plenty of people are, and that's fine. We'll catch up. So, so now here we are into part 4. Coming into part 4, which Kepler says is on the first inequality based on physical causes and the author's own ideas. The first inequality, we get this vocabulary, we have to, have second nature. The first inequality is the motion of Mars. So part 3 was about, just to review, part 2 was about the first inequality, Mars, an imitation of the ancients. So Kepler tried looking at Mars with an equant, found out why it couldn't work. Very curious hypothesis failed. Part 2, he looks at the second inequality from a physical approach. So he looks at the Earth-Sun motion. He shows that the Earth does not move at a constant speed, like everyone before him thought it did, that it changes its speed, and therefore this physical principle can also apply to the Earth, because it doesn't stand apart from all the other planets moving uniformly. It does change its speed. And then he puts in this physical idea the sun's moving the planet and everything. So now here we are in part 4. We're back to the first inequality. We're going to look at Mars again, and we're going to use this physical principle that he has not just a vague idea of, but he's put a specific physical interpretation on in part 3. The time it takes the planet to move a certain amount along its orbit is proportional to its distance from the sun. That's the physical principle Kepler's going to apply to Mars in part 4. So I broke part 4 into into 4 chunks. Today we're going to look at chapters 41 through 44, where Kepler shows the second problem back from part 2, that in part 2 he had assumed an equant and that Mars moves in a circle. He is going to, in these chapters, show that Mars definitely doesn't move in a circle. Then from chapters 45 through 50, we'll have Kepler making a guess, making a hypothesis about how the planet might move in a non-circular way. It doesn't work out, but he learned something very important from it that'll come back actually 10 chapters later. In the third part of part 4, we're going to look at Kepler doing some more investigations, making a very fortunate discovery that puts him on the right track to figuring everything out. And then in the fourth of the 4 parts, on part 4, we're going to look at Kepler's second physical principle about what's causing the planet to come closer and farther from the Sun, which, working in conjunction with the rotation around the Sun, being controlled by its closeness to the Sun. But those two put together explain everything about Mars, and then he finally determines that it moves in an ellipse. So that's what we're going to get through in part 4. Today we're going to look at the first aspect, which is showing that Mars doesn't move in a circle, and we have to start looking for a new hypothesis. So to start with, chapter 41, Kepler returns to something he had done in part 3. Remember, in part 3, he was looking at the Earth. And since we stand on the Earth, it's very hard to look at it. And the reason that nobody had made the breakthrough he had about the Earth before is that they only looked at the Sun. Now, if you're on the Earth and you're watching the Sun, you can figure out, that's all it took Hipparchus to figure out that the Earth moves eccentrically because the seasons are different lengths. You can figure something out from watching the Sun and how it moves at different speeds through the sky at different times of the year. But you can't be very precise with that. And Earth's eccentricity is very small. So in part 3, Kepler had said, well, I'll stand on Mars. If I watch Earth from the Sun and from Mars, then I've got a much better view, and I can get a greater precision than anyone ever had before, which is what he did and how he proved that what people thought was the Earth's eccentricity was actually where its equant appeared to be, and that its center was, it had a center and an equant. Anyway, so from when he had done this in part 3 to watch the Earth, the other thing that he did is it meant he had 4 very good observations of Mars. So he used the Sun and Mars to watch the Earth. Now he's going to go back and use his work on that to use that to know where Mars is very precisely, to know this distance. How far is Mars from the Sun? So he says, well, he knows from geometry that if you have 3 points, that makes a circle. So he's got from chapter 26, he's got from chapter 27 a Mars location, and in chapter 28 he has a Mars location. So he just says, okay, well, I'll put all 3 of them on a circle. He knows how far away Mars was at these 3 different locations, and what direction it was seen from the Sun in those 3 different directions. So that should be enough to do a little bit of trigonometry, and bam, he finds the circle. He finds he draws a circle through those 3 points. He gets the center, and what does that give him? It gives him the eccentricity of Mars's orbit, the distance between the Sun and its center, and where was that center? It gives the line of Apsides. So he calculates in this chapter, in 41, what the line of Apsides is and what the eccentricity is. And these are the numbers that he got. Let's see if they're on this page. No, they are, but they're not written particularly big or anything. He got an eccentricity of 9,768. The vicarious hypothesis bisected would have been 9,282. So 9768 versus 9282. It's a pretty big difference. Also, the direction of the line of Apsides he gets in chapter 41 is 1.5 degrees different from the line of Apsides in the vicarious hypothesis. So he says, well, here's exactly what he says. He says, all this, you can see it, all this is completely erroneous, as you can tell by substituting other distances belonging to other eccentric positions for one or more of the distances used. Every time you try this, by an equally certain and irrefutable argument that all those numbers come out differently. And so here's an animation of what Kepler was experiencing. Let's let it start over again. I guess that gives it away. Okay, so here we go. So, from any three positions, if you said I know where Mars is, there is a circle, a center, and a line of apsides. Kepler says if you tried three other positions of Mars that you knew, you get a different center. So how can you have both of them be true? It's if it doesn't actually move in a circle. So that's where Kepler goes with chapter 41. You're getting the hunch that this is, maybe it doesn't really move in a circle. So in chapter 42, he says, well, that means we've got to get a little bit more precise here. If we want to know how far away Mars is at aphelion and perihelion, we can't do it just by having any three old positions and draw a circle through them, because maybe it doesn't move in a circle. So if we want to know the aphelion and perihelion, we have to actually look very specifically at aphelion and perihelion. Now, already in part 2, Kepler had an estimation for how far away, in other words, back in part 2, Kepler already has an idea of the distance between the Sun and the center of Mars's orbit. He has two estimations for that. One is bisecting the total eccentricity. In other words, going from the Sun to the equant, cutting it in half, and putting the center there. That gives him 9282. Also, using the latitudes, which he used to disprove the vicarious hypothesis, he knew that the eccentricity was somewhere between 8,000 and 9943. That's a huge range. It means he doesn't really know what it is. And he's not going to count on this bisection. That's indirect. We got to actually very directly measure the eccentricity. And he has not done this before. In part 2, the closest he got to actually measuring the eccentricity, the distance from the Sun to Mars' center, by measuring it at aphelion and perihelion, best he got was that it was in the range of 8,000 to 10,000. That's not that helpful. So what Kepler does in chapter 42 is he figures out pretty closely when Mars is at aphelion and perihelion, and then he goes through Tycho's books, and he looks to see if, every Mars year, when Mars keeps going back to that same spot, did Tycho make an observation of it that day, or even close to that day? And he finds 1, 2, 3, 4, 5 times that Tycho looked at Mars when it was near aphelion. And he found 3 times that Tycho looked at Mars when it was near perihelion. So he does some work with that, some pretty clever trigonometry. He figures out how far away Mars was at aphelion and perihelion, takes the average to find the center, the difference between that, and and then he's got the eccentricity. He also does something very clever to figure out how to adjust that line of apsides, which, if there's questions about it, we can go through it, but I don't want to go through it here. He did something very clever, and at the end of that chapter, he's got a very specific idea of the eccentricity, which says here he gets 9264. He gets 9264, which is almost exactly the 9282, the bisected eccentricity. And he also gets the line of apsides, which is within 11 minutes of what the vicarious hypothesis had determined the line of apsides to be. So, why is this important? 2 reasons it's important. One, you have to know the eccentricity. Second, if the eccentricity was much different, he could not apply the physical principle of part 3. I think that's very easy to overlook. Let me say that again. If the eccentricity had come out much different, if it wasn't about approximately bisecting the distance from the Sun to the best equant location of 18,000 something. If it didn't bisect that, then Kepler's physical hypothesis in part 3 could not be applied to Mars. He requires a bisected eccentricity, because only then would it appear that the speed of the planet is inversely proportional to its distance from the sun. So very important, don't overlook it. He had to know the number, and he had to know that the number was bisected to do what he's going to do next. So then we got chapter 43.
Hey, Jason, can I ask you a question real quick?
Yeah, sure.
On that construction of Mars's orbit and Earth's orbit, and he says on there that he's taking Mars's, I think Mars's line of apsides with a diameter as 100,000. I was just thinking in my mind, because he's doing this thing that's very precise from Tycho's measurements of the Mars year to find the line of apsides. How big do you think these circles were that he drew, or like, because he's taken them out of 360 degrees and they have to be very precise. So I was just wondering how you would actually physically make this construction, if that makes any sense.
I'm not sure what you mean by make. You mean like how large a sheet of paper did he need, or what do you?
Yeah,
I don't.
Yeah, because he would have to look at all these lengths, these changes in degrees, and there'd have to be a lot of them. So it seems like it'd be a pretty big drawing or something.
I really don't know. I really don't understand what you're. I mean, he used these 5 positions to do it here, but are those, when you said, are those 5 the a lot that you're talking about, or?
Yeah, those 5 positions, for instance. Like, how would you know exactly where to find them? Yeah.
Where to find them on
a circle, where you're constructing that one circle in proportion to the other based off of all of Tycho's data. I'm just wondering, it seems like it'd probably be pretty hard to construct.
Yeah, it is. Let me do a drawing here. Let me switch to this other camera and do a drawing here on some paper. Okay, so you switch to this other, switch to the view with my pen here if you're watching this live, so you can see what's going on now. Okay, so here's what Kepler's got. He's got he's got the sun. He's got the Earth going around the sun. Okay, this looks like it's on the top of the screen. Okay, now what he's going to do is he's looking for this line of apsides. Wow, that's pretty. Anyway, whatever. It's just a vision. So here's where Mars is at aphelion, and here's where it is at perihelion. So I think he calls this one iota, and he calls this theta here, and this is alpha. I'm writing upside down, so forgive me here. Anyway, so where is this spot? And what he's looking for is this distance, right? He's looking for the distance from the sun to Mars. What does he know? Well, he's got these. Let's just take one of the triangles for now. He's got some Earth position. He feels very, very confident in this direction, in where the sun is seeing the Earth. He feels very confident in that. I mean, there's really no. Tycho felt confident about that. There's no real improvement, even though in part 3 he changes the theory of the Earth and puts an equant in it. It really doesn't change the position of where it sees the sun very much at all, just a couple minutes. So he's confident in that. He's confident in this distance as well, the Earth-Sun distance. He's very confident in that from part 3. He's very confident in this angle. This angle is Tycho Brahe's observation. He looks in Tycho Brahe's records, and he sees that Tycho Brahe says he saw Mars in a certain direction. Well, if he knows what direction Tycho saw Mars in, and he knows what direction Tycho also considered, the Earth-Sun angle to be, he knows the angle between the two. So on this triangle, he's got this side for sure, and he's got this angle for sure. The way he gets the distance from the Sun to Mars at aphelion is he says, I'm going to guess a distance here. I'm going to hypothesize a distance, and then I'm going to check it. The way he does that is once he gets this distance, he can then use the law of sines to, get all the other angles in the triangle, and he'll get this angle. Once he calculates this angle, it means that this is where the Earth-Sun line was, adjust it by this many degrees, and we get the longitude of Mars as seen by the Sun. So it's kind of a weird background. Still there. Yeah. Sorry. So to go back to this then, what Kepler's approach is that for all of these triangles from the Earth, the Sun, Earth, and Mars, if he got this distance correct, once he knows that distance properly, then the calculated longitude of Mars will be the same for all 5 observations. So that's the trigonometry he does in this chapter. He says in each triangle, just to say it one more time, he knows the Earth-Sun distance from his own work. He doesn't take that from Tycho, because he changes that in part 3. He has this distance, feels very comfortable with that. He has this angle, feels very confident in that. If you then assume a certain length for this, you'll be able to calculate this angle, which means you'll be able to calculate the direction that Mars is in. If you do that for these 5 triangles, and they say that Mars is pointing in all sorts of different directions, it means that you've got this length wrong, and you need to adjust it until they all come out the same. So that's the specific technique that he used on this one to get that, to figure out what the distance was. Does that address what you were wondering?
Yeah, thanks.
Okay. And then in all these chapters, there's a lot of specifics and a lot of detail, and we can totally go through that, and then also we can go through it more, when we get on individually. I mean, the thing that he does here to adjust the apsides it's pretty intense, and it's really very smart of him. I mean, he's a very clever guy. Okay, so we think Mars doesn't move in a circle from 41. We know its eccentricity from 42, and we know it's bisected. That means in 43 we can implement that physical principle that he discovered and applied in part 3. So now we're going to use area to measure the time of Mars. He's also going to find out how much area isn't the sum of the distances, etc. But let's basically use the area. So the way he does that is, here we go. He tests 3 different eccentric anomalies. So let's go over some of these words. This is in the homework, but I'm just, there's no point in not saying what they mean if it's coming up in the presentation here. So we see all of the different anomalies and equations are on this image here. So this is the aphelion. Here's how far Mars has moved along its orbit. That's 90 degrees eccentric anomaly. 90 degrees at the center saw Mars move. The mean anomaly, which measures the time, that's the area swept out by the planet, which is the 90 degrees from here, and whatever the area of this triangle is a portion of the whole circle. The equated anomaly is where the Sun sees Mars. And the difference between where the center sees Mars and where the Sun sees Mars is this angle here, the optical equation. The area of this triangle is the difference between the mean anomaly, the whole area, and the eccentric anomaly, just from the center. So the area of the triangle is the physical equation. The angle here on the triangle is the optical equation. Those came up in chapter 40. So equation is a difference between 2 anomalies. An anomaly is an angle, either from how far the planet's moved along its path, where the sun sees it to have moved along its path, or how long it took to move that amount along its path, or the eccentric, equated, and mean anomalies. So Kepler tries out at 90 degrees, at 45 degrees, and at 135 degrees. So these are the apsides, this is the quadrant, and these are the octants. So he tried it at the quadrant at 90 degrees and at the two octants here, at 135 degrees and at 45 degrees. So what he would do is he would, he'd do his trigonometry, he'd calculate where the sun saw Mars, and then he would take the total area swept out, that's the mean anomaly, he'd plug that into the vicarious hypothesis, meaning he would, stick in the center in the equant, go 45 degrees from the equant, and see where does the sun see Mars, and he could compare them. So he'll say, does area time work for Mars? Let's see. And so you can see that. I'll switch to the image for the YouTube viewers here. So here you can see the difference between, so the first column you get the mean anomaly. When along the orbit are we looking at it? Second column is using area time. Where does the sun see Mars? The third column is using the vicarious hypothesis. Where does the sun see Mars? And remember, the vicarious hypothesis definitely works. And then we see that difference. So we've got an 8 minutes difference. Using area time with the circle means Mars is off by 8 minutes at the octants in a specific way. Let's take a look at this. So don't worry about the blue dots for now. At the quadrant it works fine. It's 24 seconds off, whatever. Here's where Mars should be at the octant. Here's where using area time actually places it. So it's a little further from the apsides, closer to the quadrant. Here at 135, this is where Mars ought to be, according to the vicarious hypothesis. And this is where using area time places it. So Kepler makes a conclusion from this that, can anybody say why this leads Kepler to conclude that Mars does not move in a circle? And specifically in what way it doesn't move in a circle?
Doesn't he say because if he had it on the line of apsides and it moved on a circle, it wouldn't speed up and slow down? Something like that? That it would, because at the first octet it speeds up and then at 135 it slows down, so that maybe the sides come in like an oval, something.
Well, yeah, I mean it does speed up. Kepler wants it to speed up and slow down. That's his. Maybe that just wasn't very as specific as it needed to be. I mean, it changes its speed, but in what way does it change its speed in a way that suggests how it? This is a totally leading question, huh? Anyway, Ray, were you about to say something?
Yeah, I was going to say something along those lines that, pretty much it was you had different calculations that were close, therefore it couldn't be a circle because you had the different speeds as Cameron was going through. But that's pretty much what I was going to say.
Okay. Well, I mean, I guess, yeah. I mean, it would have worked. If this worked, it would have worked, right? If it's off, then it's not right. So I guess that's, that's one, that's a pretty clear thing. The specific way that it, the specific way it doesn't work suggests to Kepler that it actually should be squashed in on the side, because Mars moved too fast up here, according to the circle and his physical principle. Mars moved really fast up here, got too far ahead of itself, and here it goes slower. Right? The distance it should have gone from black spot to black spot is larger than the distance it did go from the red spot to the red spot. It's too slow here. If we pushed it in on the sides, it would get closer to the sun, and it would speed up. So that leads him to. So then basically he just puts 2 and 2 together in chapter 44, and he says both for reasons of distance that Mars is closer based on the eccentricity. You can calculate how far away would Mars be from the sun if it were on a circle. And it's not that far away. It's closer, especially over here. It's pulled in a certain amount. So based on that and the fact that it goes too slow in the middle longitudes there, Kepler concludes it's not a circle. It's got to come in on the sides, and we're going to have to make a hypothesis about how it can be in a different shape. He says in an oval shape, a very generic word. Ellipse is a specific geometrical word. Oval just means it looks like an egg. So, okay, so that's what these 4 chapters cover. So I think the thing to do now is see if there's any questions, and I guess I could also just review what the homework questions were. Not answer all of them, but just go through what those questions were. So let me just look back at what those what questions came up here. Let's see here. I'll just read them. Can you construct a circle that goes through any 3 points? Okay, there's one. How did Kepler decide where to look in chapter 42? Where to look for aphelion and perihelion? How did he choose to use those 5 observations for aphelion and those 3 for perihelion? Why did he use those? What does it mean when Kepler says that Mars is leaving its station? Is it catching a train? There is to redo the calculations in 43 for the eccentricity of either 45, 90, or 135. Recalculate the mean anomaly there and the equated anomaly, and then plug in the mean anomaly to the vicarious hypothesis and see if you get the same thing. Just double check and see if you got the numbers that Kepler did. Explain why this means that Mars doesn't move in a circle, and do you think his demonstration would be convincing for all astronomers? So, Jim, almost a lot of those we covered, at least just right now, we're mentioned in this discussion. But all right, I wanted to stop there and leave a lot of the time for questions.
Hey, Jason?
Yeah.
I was just wondering if you could sort of go through again the last chapter, or I'm sorry, 43, where he's comparing the different locations that the planet would have to be through the different methods.
Yeah. Maybe we can just do one of these together. Maybe we can do the 45-degree one together, and it's good to work through how to do the math together. So let's take a look at this. Okay, how do we calculate this? Why don't we go ahead and do the 90 degrees one, and as a start. So just to say what those 3 anomalies were again, right? We've got the eccentric anomaly. In this image, it's 90 degrees. We've got the equated anomaly. Well, we've got to calculate that. And we've got the mean anomaly, which is the area swept out, which we got to calculate that too. So we need to do that for this, and then we got to plug it into the vicarious hypothesis. So we can do both. I included a I included a spreadsheet. Let me open up this spreadsheet here. I made a spreadsheet for you to make it a little bit easier how to apply things to the vicarious hypothesis. Let me open up that spreadsheet too. Make it big enough to read. Okay, good. So let's cut off a little bit. Okay. Okay, so let's go ahead and do this example. Let me switch over to this other camera. All right, so if you can click on that one that's looking at the page there if you want to watch it. And I'll twist over this way so I can write on it. So. So what we got to do is find this whole area. Right? Well, how much is the area of this of the circular sector? Just so you know, the word sector always means a circular portion. So how do we find the area? What's the area of this circular portion here?
It's the ratio of the angle of which it's the ratio of the equated anomaly to the angle of the whole circle multiplied by the area of the whole circle.
Yeah. So what is it for 90 degrees here? What is it going to be?
1/4.
Right. So the area of the shaded area, the sector, is going to be 1/4 times pi, and so on, times the radius squared. Should have written this bigger. The radius is 100,000. So Kepler, let me flip open the book here. So Kepler, he goes ahead and he does that. Let's see here. What does he say it is? So the area of the okay. He says the area of the whole circle. Okay, the whole circle is 31. Is that a billion? I guess 31,415, 926, 536. That's the area of the whole circle. Okay. So we're going to have 1/4 of that at 90 degrees. Okay. Now the area of the triangle is okay. What's the area of that triangle? What is the area of any triangle? It's half the base times the height, right? So our little triangle is going to be 100,000. That's the radius of the circle, divided by 2, times 9,264. So that comes out to 463,200,000. Okay, let's put that together to get the to turn that into a mean anomaly. So let's switch over to let's use a spreadsheet for this, or just any kind of calculating thing. I'm going to use this so that we can all see it, though. Okay. So the area of the circle was 31,415,926,536. Make a little bit more room. Okay. The triangle is 463,200,000. 200,000. Make sure I turn the commas on so I can see those. Okay, good. Oh, my head. Okay. Can you? Okay, make it a little bigger. You guys can see those numbers, okay? All right.
Yes.
Okay, so at 90 degrees, when we're at let's do it at 90 90 degrees, we'll have like 1/4 circle and the whole triangle. So let's see, 90 degrees. Well, we can do all of them. 45 degrees, 90 degrees, and 135 degrees. And let's put the area that got swept out here. So 45 degrees, we'll take the circle, and we'll divide it by 8. Let me switch that other camera just to make that screen big so you can definitely read it, okay? Okay. Okay, so here we've taken 1/8 of the circle for 45 degrees. We'll have the sector part and the triangle part. At 90 degrees, it's equal to the whole circle divided by a 4, right?
Jason,
Yes.
we can't see the screen. Well,
You have to click on the Jason thing at the bottom.
we did, and it's just a different camera view of you.
Oh. Oh.
Thank you.
Do you see it now? Oh. Is it working now?
We've seen it.
Yes, it's working.
Yeah.
Okay, good. Okay, so in 135, we're going to take the circle, and we're going to have 3/8 of it. There's that formula there. Okay. At 90 degrees, the triangle, we have the whole triangle. How much of the triangle do we have at 45 degrees? How tall does the triangle become at that location?
Well, the triangle's it's as high as the radius.
Right.
At 45. I'm sorry.
Mhm.
Isn't there a special relation? It's like 1 square root. I can't remember the formula for the special triangle there at 45.
Well, the special thing is it's 1 over the square root of 2. More generally, it's the sine of the angle there. Right? You can see at the picture on the screen, you've got the whole radius at 90 degrees. That triangle is not as tall at 45 degrees. Its height, that green dotted line, is as the sine of the angle that it's at. Right? So let's go ahead and do that for our calculation. Let me switch over to that now. So we're going to take the whole triangle times the sine of, sorry, you have to type this into it instead of just typing 45 directly. Okay. So that's the amount of the triangle at 45 degrees. It's the same at 135 degrees. Same height. So if we look at the total area, it's both of those put together. Whoops. And it's the same for the other two. It's those sums. Put those commas back on. Okay. Now we've got to turn these areas into degrees, right? to do that, does anybody know how we would turn this area into a certain number of degrees? Any ideas?
From the sun or from the center?
This is the total area swept out as the planet goes around the. Let me switch over to this. If you go to the view of me instead of the worksheet now, the area swept out from the sun, that the planet sweeps out from the sun, is composed of this circular sector here, which is 1/8 of the circle, and the area of this triangle. So what we were doing in the spreadsheet was we were adding the area of the circle, or 1/8 of the area of the circle, and the area of this triangle, and we got a total area when we were done doing that, right? So in the spreadsheet we got an area of 4,254,000,000. So that's an area on for when the circle has a radius of 100,000. We have to turn that area into a certain number of degrees to turn it into a mean anomaly.
Hey, Jason,
Yes.
couldn't you take the whole area of the circle with the total area swept out, and you can create a ratio between that and then 360 degrees, and then find what the degrees are for what was swept out? Does that make sense?
Yeah, I think I understood you right. You're saying take this area as compared to the whole area?
Yeah, take the whole area of the circle, the 31,415,000,000 da da da.
Yeah.
And you create a ratio between what was swept out at 45, which is 4,254,000,000. So it'd be that 4,254,522,678 over 31,415,926, and create a ratio that would be equal to something over 360. And you just solve for x. Solve for that.
Right, which the way to do that would be to multiply it then by 360. So you just have x by itself.
Okay, yeah. Yep.
Right, so let's do that. So in the spreadsheet, yeah, we'll take that 4 billion whatever, divide it by the 31 billion, and then multiply that answer by 360. And here's what we get. 48.753 whatever. So that's the mean anomaly. It corresponds to the eccentric anomaly of 45 degrees. Let's do that with these other ones too. Okay. So then we've got these. We've got this mean anomaly here. Now let's just do a quick reality check to make sure that that what we're doing is similar to Kepler. So it's a good idea to just double check your along the steps. Whenever Kepler gives numbers along the way, just see if you're in the same ballpark as him. And he had said that the mean anomaly. Oh, it was on the web page too. He had said that right, these are the mean anomalies that he got. I'll just read them, and if you can't see them, I don't know. He got 48 degrees, 45 minutes, 95 degrees, 18 minutes, and 138 degrees, 45 minutes. On our spreadsheet, we got 48 point something degrees, we got 95 something degrees, and we got 138 and something degrees. Those are the same numbers that it looks like it's we don't have minutes and seconds here, but those are the same numbers that Kepler got, which means that we're probably doing the right thing. So what we would now do is take those. Oh, we still have to calculate the equated. We still have to calculate where would the sun see Mars too. So how do we do that? Back to that picture. Well, for example, 90 degrees, what's this angle here? How do we figure out what this angle is?
Take the inverse tangent of the eccentricity over the radius.
Right. Right. Let's go ahead and do that. It's easy for 90 degrees. The other ones get harder. So, and that's called the optical equation. And at 90 degrees, it was the inverse tangent of 9264 out of 100,000, it said. Yeah. You'll find out if you're using, maybe Excel uses degrees, but at least for LibreOffice Calc, it doesn't use degrees, it uses radians for angles. So you'll find that if you're doing sines and cosines, things might not come out like you expect. So what you have to do is, this is a tan, arc. I mean, it's the opposite of the tangent. It's the arc tangent is what the word comes from. It gives you radians. So you have to say how many degrees is that if you're doing your spreadsheet. So we got 5.25 ... degrees. So we'll now have the, this is the mean anomaly, the optical equation. So the equated anomaly is equal to, it's 90 degrees, and then is it plus or minus those 5 degrees there? Is the equated anomaly 5 degrees more than 90 or 5 degrees less?
What's the equated anomaly again?
The equated anomaly is where does the sun see Mars? So we just calculated this angle, the optical equation, by doing that tangent as you had said. And we got us 5 degrees and something. So what's this angle? What's the equated anomaly?
90 minus that angle, the optical equation.
Exactly. So 90 minus that optical equation. So 84.7 degrees. I've got another spreadsheet here, which I shared. I'll put this in I'll add this to the homework document so you can play with it also. Here's another one where I've got a, let's switch the view. Let's do this. Okay. So if you're looking at the close-up there, just show what it's like to plug it in. So we had a mean anomaly of 85.307. If I plug that in here, 85.307, it says I got an equated, whoops, I guess I made this spreadsheet wrong. Huh. Okay, looks like we got a little problem here. No.
What happened?
A minus should have been a plus. Okay, there we go.
Typical math
Plus or
error.
minus.
So this came out, let's just see if that's right. So this came out to 83 degrees. This was 84.7 degrees. Okay, obviously there's a mistake here in what I did. So, yeah. Okay, well, back to the drawing board, I guess. Well, are there, I hate to kind of leave that one in a mess, but it sort of is right now. Let me make sure that's what Kepler got. 84.7 degrees equated 90. Is that what what the?
Hey, Jason, was it 85 or 90? I thought it was 95. No.
No, it should be 85 because it's less than the equated anomaly is how far does the sun think that Mars has moved? If it was down here, then it would have an equated anomaly of 90 degrees. But as far as the sun's concerned, it has not moved 90 degrees yet. It's moved less than 90 degrees.
You're talking about the
Could you say that again?
one that's
You had
which one were you using? What one were you trying to plug in?
your audio just dropped, so I'm not sure if I was getting this equated anomaly here, which is the 84. We got it like 84 degrees, or what did we get? We got that should have been 84.7 degrees. Right here. And then comparing that to what Kepler got, he says that he got 84 degrees and 42 minutes. So we got that one right. 84.7 degrees sounds like 84.42 minutes. All right, so that works. The trouble is going to be now we got to figure out how to use the vicarious hypothesis to get that equated anomaly also. Which we could do. I kind of want to see if there's other questions because this will take the rest of the time doing this calculation. But it's it's good to do something in depth. So let me ask, are there any? I'm fine with. I think it's a good idea to go through this. Are there any other parts among these 4 chapters or general things that people have questions about, or should we go ahead and do this calculation here? Okay, well let's do it then. First, let me show you how to turn this into degrees, minutes, and seconds. Now, I really recommend using a computer. Actually stinks. Using a calculator is much better. There's a lot of good calculators. You can get them for not very much money at all, and they do degrees, minutes, seconds by themselves. It's so convenient. But so let me show how to let's turn this into degrees, minutes, and seconds so we can compare it with what Kepler did. I guess this is going to become a bit of a how to use Excel class here. Or maybe let me just do it. I don't. I think we should focus on how to use the vicarious hypothesis and not how to use Excel. So let's just get this real quick to make sure that we're right here. Whoop. So 84 degrees. 42 minutes. And, oops. 84, 42, 26. And he had gotten 84. That's exactly what Kepler got. 84, 42, 26. That's what he got using the area time. So that's good. Now let's go ahead and do the vicarious hypothesis and figure out what we would have gotten for that. So I'm going to use a nice sheet of paper for this and switch over to this other camera. Okay, good. So what do we have? We've got a mean anomaly of. First off, let's go ahead and draw our vicarious hypothesis here. So the eccentricity of the eccentric is 11,332. The eccentricity of the equant is 7232. So what we know is we have a mean anomaly of 95, whatever it was, degree. How many? What was that? What was that mean anomaly that we had? 95, 18, 28. Okay. So this angle here from the equant is 95, 18, 28. So the question is then, we have to find the eccentric and the equated anomaly. Anybody remember how to do this? Have we done this before? Is that big enough? I don't think that's even big enough to see, is it? Let me draw it larger.
Yeah, Jason,
Yeah.
isn't that a squared plus b squared equals c squared?
Well, that's if you have two sides of a right triangle. There's no right triangle in this drawing. We do know this length, we do know. This is 100,000. This is the radius coming from the center. Right? We know what this angle is also. It's just 180 minus that 95, 18, 28. We know this side is 72, 32. So what can we use to figure out the rest about this triangle? What can we use to figure out what the what this eccentric anomaly is here?
I think you can use the law of sines.
Exactly. Right. Yep. We know that the sine of 180 minus 95, 18, 28 over 100,000 equals the sine of, let's call this angle A, equals the sine of A over 7232. Can anybody punch that out on a calculator? Should I go ahead and do it? Okay, I'm doing it. Okay. So this is what here's what I got, 4.13 degrees for A. So now we also know this angle here. Since we know two of these angles in the triangle, we can also get the third, which we take 180 from to get this one. And then in this triangle, we've got, right, This side's 100,000. This side's 11,332. And we have the angle in the middle, which means what do we have to do to figure out the rest of that triangle? We have to use the dreaded law of tangents. Now, I really don't like the law of tangents, so,
I was just going to make a groan.
There's ways of getting around it. I mean, one way you could do is you could drop a perpendicular from here and then, get the. Anyway, I really don't like it. What we can do is, well, first off, so let's get this. Let's go ahead and get this angle here. I'll call this angle B. Let me just do these subtractions here on the computer and get what B is and tell you what that comes out to. So that equals, so we got 180 minus the 95 degrees there minus that 4 degrees thing there. Okay. So I'm just going to draw the one triangle by itself. Here's a repulsive rendition of this triangle. We have the sun, 11,332. This angle is 99.437 degrees. And whoa. Okay, yeah. And then we got to figure out what what this angle is, what the equated anomaly is.
If you don't like the law of tangents, you can use the law of cosines.
I am going to use the law of cosines. So
All right.
Yeah, no, I'm with you. The law of tangents is terrible. So the way to use the law of cosines for this is you first find the length of that opposite side by saying that the one side squared plus the other side squared minus 2 times the side times the cosine of the angle in between them is the square of that opposite side. So I'm going to go ahead and do that. So we got the square root of 100,000 times 100,000 plus 11332 times 11332 times 2, plus 2 times one of the sides, 11332, times 100,000. Oh, you can't see what I'm doing anymore. Put that sharing thing back on the right way. Okay. Times the cosine in radians of the angle between them. We get 9877. Wow, that can't be right. Oh, minus, right. Okay, 102,469. Is that the long side there? 102,469.665 or whatever. Then we can use the law of sines to get the equated anomaly, which comes out to, what do we get for that? We get that that is the 100,000 times the times the sine of that angle divided by that 102 number. Wow, and that's just definitely not right. Should have been 84 degrees. Well, this just goes to show you, I mean, you know, imagine, I mean, the amount of work that Kepler had to do to put this book together, and then here we are with computers getting screwed up by something this easily. Pretty amazing.
Yeah, he would waste 3 months, and he made one mistake, and 3 months of calculations. He had to go back do the whole thing over again.
Yeah. All right. Well, I'm just not sure how much. If this is this what people would like to spend their? Is this okay to be doing this? Like, is there any other questions people have, or I don't know how long we ought to be going either. Let me do this. Let me go ahead and say what's going to be coming up for the next time, and then I'll keep doing this until I get some numbers for this. And if you want to stay on, then you're certainly welcome to. Just to review from these 4 chapters, we've got that Mars doesn't move in a circle. That when we try to make it move in a circle, it's too far from the sun. That the real distances are closer on the sides. And that making it move in a circle makes it go slow on the sides. That it really ought to be going faster there, which would be fixed by bringing it in. Just as I suppose, a teaser for what we're going to be going through in the next sections, let me just show an animation of his next idea in chapter 45. If you remember back in chapter 39, Kepler discussed how really difficult it would be to have the planet, to have an epicycle that changes its speed in the same way that the planet is going faster and slower around the sun in order to keep it moving on a circle, how hard it would be to move in a circle. Kepler says, you know what, I'll tell you what. Have the planet go around the sun, but we'll have it sit on an epicycle that moves at a constant speed. And if you do that, if you've got an epicycle that's moving at a constant speed, it's rotating at a constant speed. If you watch the angle along it, you can see that. While the whole epicycle itself goes around the planet, it goes around the sun, faster when it's close, slower when it's far. The combination of those two will end up pulling the planet in on the sides and making it have an oval shape. So, you know, Kepler knows this is not the greatest of ideas. He knows this can't really be true. But just to pull ourselves out of the details for a minute, I mean, where do you go? You know, what do you have to go with once you've got all you know is that Mars doesn't move in a circle, that its speed as it rotates should be based on how close it is to the sun. You have nothing, no idea what changes how close it is to the sun, what makes it get closer and farther. I mean, has his thoughts of part 3 and the physical power of the sun, they're not going to help him with this.
Hey, Jason?
Yeah.
Do you remember earlier in the book, Copernicus' double epicycle? And how, I forget, was it that it pulled it in too much? Because he said that actually if you have the double epicycle, it wasn't a circle.
Right, the double, yeah, let's show a picture with that. Uh-huh.
Was it too, was it pulled in or was it too fat?
It actually,
I don't remember.
Here you see, no, I'm not seeing the picture of it. Oh, there it is. The double epicycle's the red, and you can see it actually, it puffs out on the sides. This is the Copernican, or also Tycho. Sort of the biggest impact that Copernicus had in astronomy was that people liked his double epicycle way more than they liked his idea of the sun being at the center. So to avoid the equant, he used 2 epicycles. He actually had more epicycles than Ptolemy. It turned, if you do all this, to make the planet appear to change its speed. It pushes it out, though, because that's something that Kepler brings that up in that chapter. But he says that wouldn't help it. With this double epicycle kind of idea, the planet gets further out at the middle longitudes. Now here you can see it. The planet's pushed outwards on the double epicycle. So that that combined with his power of the sun moving the planet would make it actually go slower there than the circle, and it needs to be going faster there than the circle. So that wouldn't help. He brings that up for anybody who's complaining about, well, yeah, the equant, though, I never believed in that anyway. What if it was a double epicycle? And he says, well, forget it. So he kind of makes fun of himself for this idea of this constantly moving epicycle somehow being the cause for the planet moving in and out away from the sun. But, it's kind of tough to get upset with him because, what does he have to go on? And what else is he going to do? He has to try something. No, this is not. There it goes. Nope. Anyway. All right, I'm going to end it there for the YouTube aspect of things, and we can keep doing this calculation if you'd like to. But just so, so for next time, the homework for next time, the reading guide and the homework is not up yet. It's a lot of chapters. And, it's so many, there's just no way we're going to read all those chapters in the amount of time that we've got. So it's mostly going to be looking at the websites for a couple of them because they're very, very mathematically involved, very, very difficult. And anyway, so that'll be up by tomorrow for sure. I'll send you guys an email when it gets when the Google Doc gets updated. It's already there. The first half of it's already there, so you can go ahead and start taking a look at that. And otherwise, I will see you on YouTube next week with chapters 45 through 50 of part 2.